Today we're going to take a look at something called projectile motion. Projectile motion is quadratics in action. So it is the path that something might take if it was launched or dropped from a height. So in this image, we have a building and something is being launched off the edge of the building. So if I was looking at the key features of this particular path of the object, I have my y-axis and I have my x-axis. As the object is being launched, my y-axis is going to represent the height of the object, while my x-axis is going to represent the time that the object was in the air. So if the object is launched from the edge of the building, this one would be my y-intercept or my starting point. Sometimes the starting point is at the origin at 0, 0 if something was launched from the ground, and it could be at a height of whatever depending on where the object was launched from or thrown from. The object in this case reaches a maximum height, which the key feature that we'd be looking at here is my vertex. So this is the highest point that the object will reach depending if it was launched or thrown. Here at the vertex, gravity kicks in, and that is what causes our object to fall back to Earth. When that object hits Earth or hits the ground or whatever horizontal surface that we are looking at, this would be considered my x-intercept. All of these are going to be the same. You can call it an x-intercept, you can call it a zero, a solution, or you can call it a root. Any of those mean where that object intersects the x-axis. And then the space under that quadratic is time. So how many seconds did it take to reach the maximum? How many seconds did it take to reach the ground? Or how many seconds until the object is 8 feet off the ground? Different things like that. So we're just looking at key features with quadratics in action or in movement. So I have a couple word problems, and I also have Desmos, my graphing tool that I use instead of having to do the math by hand. So a soccer ball is kicked from the ground with an initial upward velocity of 90 feet per second. Basically what that's saying is a soccer ball was kicked really, really hard. And the equation that we're going to be using is h equals negative 16t squared plus 90t. When we're working with projectile motion, your equation is always going to be given to you, always. And when we graph that, we can't graph it in Desmos using h's and t's, so we replace those with x's and y's. So if I was to come over here into Desmos and begin graphing, I would type this in as y equals negative 16x squared plus 90x. So in my Desmos here, the red represents the soccer ball. Now I also like to go ahead and plot my x-axis and turn it green. Just for visually, this reminds me, okay, this is the ground, so green grass. So the soccer ball started at 0, 0, and it was kicked all the way up to its highest point, and the highest point is 126.6 feet. And so let me get my pencil. If I was looking for the maximum height of this soccer ball is 126.6-ish feet. And if I wanted to know, well, how long did it take for it to reach that, I would look at my y-coordinate in Desmos and say the y-coordinate the x-coordinate, is time, and the y-coordinate is height. So my time is 2.8 seconds to reach a height of 126 feet. Part B of that question asks, how many seconds until the ball reaches the ground? So earlier I was looking at vertex. Now I'm looking at what are my zeros or my x-intercepts or my solutions. So if we're looking at the graph, the ball has traveled all the way up till it reached a maximum height, and then gravity kicks in, and then that ball starts to fall all the way back down to the ground, and it takes a grand total of 5.6-ish seconds in order for that ball to hit the ground. And so we're just looking at the different, let me write this out, the different features and how we can apply them to different scenarios. The same is true, let me kind of slide that back down. The same is true if we looked at the second example here with an apple. So an apple is launched directly upwards at 64 feet per second from an 80-foot platform. So here's what that picture might look like. Somewhere 80 feet up in the trees, somebody is going ziplining. Let's just kind of make up a story. And they have an apple in their hand, and they say, hey, you can't have the apple. So they toss the apple up, and then it comes down, and it hits the ground of wherever they're ziplining, right? The equation for this apple's height is this whole mess. So part A is asking for maximum height, and part B is asking how long until it reaches the ground. So if I was looking for key features, maximum height always means vertex, and reaching the ground is always going to be where my zeros or x-intercepts are. And so now that I have kind of a better picture of what's going on, then I can go into Desmos and use the graph to help me identify those key features. So here I would change my equation to match that of the apple. 64x plus 80. And this time when I'm looking at it, green is still my grass. If I look at my graph, it does plot a couple of these points. So if I look at the first point, 0, 80, this is saying at 0 seconds, so we have not even thrown the apple yet, the apple is 80 feet off the ground, as it should be, because I'm just standing there with an apple in my hand. Then I throw the apple up, so kind of get started here. So it's at 80, and I throw the apple up to 144 feet. And so the maximum height, or the vertex, for this particular apple is 144 feet. Now, from the time I tossed the apple up until the time it reached its height was 2 seconds. So I toss it up, 1001, 1002. That's when it reaches the highest it's ever going to reach. Gravity kicks in and starts to pull that apple back down to the ground. So the apple's falling, the apple's falling, the apple's falling. And when it hits the ground, it has been a grand total of 5 seconds from the time I threw it up to the time it hit the ground. So for part B, how many seconds did it take the apple to reach the ground? It took 5 seconds. We can still use the graph to identify other pieces of information that are maybe outside of those key features. So for example, if I look at number 4, so it says a penny is dropped off the Empire State Building, which is 1,250 feet tall. If the penny's pathway can be modeled by this equation, how long will it take for the penny to strike a 6-foot person? So this time I don't want to go all the way down to the ground. I want it to stop 6 feet above the ground because somebody is going to catch that penny. So here's what the picture might look like. Here's the Empire State Building. And somebody is hanging up at the top, and they have thrown a penny off the edge, and someone at the bottom is going to catch it, but that person happens to be 6 feet tall. So I want to start off by first looking at the path that this penny might take. So I come into Desmos, y equals negative 16x squared. That represents gravity. So anytime that you see that negative 16x squared, that's just gravity. Plus 125 250. So here is the height and the path that this penny would have taken. Scrunch it down. It's going to be kind of tiny. So way up here is the top of the Empire State Building. And we toss that penny off the Empire State Building, and it's coming all the way back down to the ground. The problem is I don't want it to hit the ground because the ground is right here at 0. So it would take 8.84 seconds to reach the ground, but I don't want it to reach the ground. I want it to reach 6 feet because somebody's going to catch it, somebody who's 6 feet tall. Well, earlier we had mentioned the X and we had mentioned the Y. X represented time, the X-axis, and Y represented height. So what I can do is draw an equation or a line that represents a height of 6. Since Y represents our height, I can have my equation be Y equals 6. So in Desmos, red is matching the pathway of the penny, and the blue is representing somebody who's 6 feet tall. And what we want to do is we want to look at where does that 6 foot tall person come in contact with the penny that's been thrown off of the Empire State Building. So here the penny is still falling, and right here is where it comes in contact with somebody who is 6 feet tall. And so we can say, well, how long was the penny in the air before that person was able to reach out and touch it? And that is 8.82 seconds. So somebody at the very top of the Empire State Building drops a penny, and roughly 8.82 or almost 9 seconds later, somebody who's standing 6 foot tall can catch that. So even though that was not a key feature, it wasn't a vertex, it wasn't a 0, it wasn't a y-intercept, it wasn't an axis of symmetry, it wasn't any of that kind of information or key features, we can still use Desmos and graphing and the different tools that we have to draw conclusions based off of a path that an object would take. Another example is number 7. So Eva is jumping on a trampoline, so I might draw a trampoline. And this trampoline has a safety net because, you know, safety first. And Eva is on the inside and she's jumping around. It says that her height can be modeled by this particular equation. So first off, let's take a look and see what does her jumping pattern look like. So y equals negative 16 x squared. There's gravity, plus 20x plus 6. So here's what she looks like as she is jumping on the trampoline. So she starts off at 0.6, which means she has not even jumped yet. She takes one great big jump and we reach the highest point. Oh, I've left out a whole number here. There we go. I knew something didn't look right. So she starts off at 6 feet. She gets one good jump in, and the highest that she's ever going to reach is 12.25 feet. So that's her height, the highest that she's ever going to reach. It takes her a little over half a second. And the question that we are being asked is, would she ever reach a height of 14 feet? Well, according to this graph, the highest that she is ever going to be able to reach is 12.25 foot. And so unfortunately, she is not going to be able to reach that. So even though, you know, the last one with the Empire State Building was not a key feature, this one we could use their key feature to draw a conclusion about her maximum height compared to, let's say, her goal height. And so it's just getting comfortable with Desmos, getting comfortable with your key features, and knowing how and when to apply them.